Okay, so today the video is called Intro to Exponentials and Logarithms. We're just going to talk a little bit about a couple of sample questions, and we'll cover more of this stuff in class. So one of the sample questions would be, given the following table of values, state which represents an exponential, and write the equation that fits the data. Okay, so if you remember first differences, what you're going to do here is you're actually going to perform finite differences. You're going to perform a finite difference technique here, and in the end, that's how you're going to end up solving this. So I'm going to go in on the finite differences here. And so you recall, you subtract the previous output with the following output. And so I'm going to go 0.75 here, 1.5, 3, 6. So I get 1.5 minus 0.75. Now 1.5 minus 0.75 is 0.75. 3 minus 1.5 is 1.5. 6 minus 3 is 3. And 12 minus 6 is 6 here. Alright. And then if you notice that there's a pattern here, then basically you want to look for, okay, now before you move on to do the other finite differences, you actually want to see what is it that is getting me from this number to this number. I'm multiplying by 2, I believe. If I take this and multiply it by 2, I get this. If I multiply by 2 again, and then multiply by 2 again, then therefore, since this pattern exists, if this pattern exists, then it's exponential. Okay, let's look at the other one here and see why this one is not exponential. So I will again perform the first differences. Subtract 5, subtract 0, subtract a -1, subtract a 2. 5, 0, 1, 2, 5, 0, 1, 2. Okay, looks good. So this is a -5. This is a -1. This is a 2 plus this is a 3. And this is a 2. So notice that there's no common product here. I can't take 5 and multiply it by something to get this. I mean, I can multiply it by 1/5, right? But then I should be able to also multiply this by 1/5. Okay, but since I can't, then therefore this is not exponential. Alright, so let's go back up to the one that was exponential. Now I need to make an equation here. What I'm going to do here is I'm going to see about making a, I gotta look at this data here. And notice that the number is times 2. So therefore my equation is y is equal to maybe some kind of stretch. The base is 2 to the x, and then maybe also some sort of shift as well. Okay. Along those lines. But I'll check it out. Check out a stretch here. Okay, now notice when I plug in a 0, I get out a 3. Alright, that implies that this could be a 3. Because what I want to do is I want to solve for the a value here. So notice right now my function is y is equal to a times 2 to the x. Remember, this 2 comes from the fact that this exists here. And what I want to do is I want to test out a few of these values. And so I would like to see if maybe I want to solve for a in a couple of these. I want to plug in 0 for x and get out a 3. So 3 is equal to a times 2 to the 0. Alright. And I want to do this for maybe another one as well. So I'll do 1.5 is equal to a times 2 to the negative 1. And I want to see what a value I get. If I can get the same a value for both of these situations, then that's going to be my definitely my a value. Alright, so it looks like in this case a is equal to 3. Notice I used x as 0 and y as 3, because over here x is 0 and y is 3. And here I'm using x as negative 1 and y as 1.5. Okay, and so 1.5, by the way, is 3/2 is equal to a, and 2 to the negative 1 is 1/2. I can cancel the 2's, and again I get a is equal to 3. So therefore my equation must be y is equal to 3 times 2 to the x. And then you can test this for some of the other ones and make sure that it works. Okay, so we just discovered what it was to be an exponential. The base is here, and then we built an equation. Alright, let's move on to another example. Here I've got a graph rather than a table of values. Write an equation for this exponential function. Okay, I notice that my graph here is at 1, or sorry, when x equals 0, when x equals 0, y equals 1. When x equals 1, y equals 3. When x equals 2, y equals 9. So I'm going to just go ahead and make the guess that my graph is y equals 3 to the x. So if I plug in a 1 here, 3 to the 0 is 1. If I plug in a 1, sorry, if I plug in a 0 here, 3 to the 0 is 1. If I plug in a 1 here, 3 to the 1 is 3. If I plug in a 2 here, 3 squared is 9. So this looks to be like the graph. Now, that part was pretty simple, but now we want to talk about what it means to be the inverse. Remember that an inverse function is graphically reflected around the y equals x line. And so, what I mean by that is if you produce a y equals x line, and the y equals x line is this, if you produce one of these lines, and then you have you reflect around it, you will always end up making the inverse of your existing graph. Okay? And so this is y equals 3 to the x. Now I'm going to reflect. Remember, reflecting around this just takes each point and takes the x's and the y values. So if this point right here is 0, 1, then on the inverse it should be 1, 0. If this point here is 1, 3, then on the inverse it should be 3, 1. If this point here is 2, 9, then on the inverse it should be 9, 2. 9, 2. And then if this one is, it looks like it's maybe, I know for a fact that it's 1/3 because of my graph. X, if I put in a -1 in, -1 is right here. If I put in a -1 into my original equation, 3 to the -1 is 1/3. And so I end up with things like 1/3, and I get my asymptote. And so this right here would be the inverse function. And it turns out that this is going to be called y is equal to log of 3 to the x. And so these two things are inverses of one another. And so that brings us to our first point of this chapter, is that exponents and logs are inverses. And we'll discuss that more in detail throughout the entire chapter. Okay, but as far as answering this question is concerned, we wrote an equation because we just tried to figure out what type it was going to be. Then we graphed the inverse by reflecting it around the x-axis. Okay, and there you have it. That one's a simple one there.